Hey Precalc, this is Limits Day 5. We're going to be taking a look here at some formal definitions today of what it means to be continuous at a given value of x. And we're going to see how limits play a role in that definition. We have at the very start of today's notes a somewhat crazy looking intense piecewise function of some sort. And what I would like you to do is, after I give you some quick direction here, hit pause and then try this page on your own, because I think you'll be able to answer a lot of the questions. It says right below this to consider the informal definition of continuous while examining the following examples. What do I mean by the informal definition of continuous? Well, in the beginning of the year, when we talk about functions in general, we say that continuous means that you can draw the graph without picking up your pencil. Okay, so clearly this graph has some issues, right, with continuity, but it's not discontinuous everywhere. So when I ask you for a specific value of x, whether or not the graph is continuous there, what I want you to do is see, can you draw your pencil through that part of the graph without lifting it up? And if that's true, then you'll say, yes, it's continuous. If not, you'll say no. But there are two follow-up questions. One is a limit question, and then one is the function value. Remember that in all these limit questions, none of them are one-sided limits. So for example, the first one, which is talking about x equals -11, in order for the limit to exist, you have to make sure that coming in from the left and right-hand side of -11, you're approaching the same y value. Okay, so when you're looking at a graph, you have to be cautious that if it's not a one-sided limit, that you have to think of that in advance. Go ahead and hit pause, try this page. As soon as you're done, hit play, and then you'll see how well you did to answer these questions. All right, let me show you the left column first. So number one, taking a look at as x approaches -11. First of all, are we continuous at x equals -11? I think so. I can, draw the graph through x equals -11 and never pick up my pen or pencil. The limit as x approaches -11. I estimated it to be -0.5. If you have something in between, 0 and -1, that should be fine in my opinion. And then f of -11 is also -0.5 in this case. All right, moving on to x equals -8. Can I draw my pen or pencil through -8 without picking it up? No, as soon as I get to -8, we have that open circle. And in this scenario, I have to kind of come up here, fill in the dot, and then keep going. Even if this closed circle wasn't here, I'd still kind of have to jump over the hole and then keep going. So it's not continuous at -8. The limit is what am I getting closer and closer to from the left and right-hand sides? We're getting closer and closer and closer to -6. Okay, so as we approach -8 from the left and from the right, the y value is getting close to -6. F of -8, though, is -3, where the closed circle is. What about at x equals -2? At x equals -2, the limit does not even exist. And that happens in other cases as well. Coming in from the left of -2, and then coming in from the right side of -2, we're not headed to the same place, are we? One has a finite value. Actually, the other one looks like it's headed up towards infinity, but they definitely don't match. And then f of -2 is 3. Moving on to the other side, number 4, are we continuous at x equals 3? I said yes. I can draw the graph without picking up my pencil there. The limit as x approaches 3, coincidentally, is also 3, and then f of 3 is 3. Moving on to 5, are we continuous at x equals 6? I think it's pretty obvious at x equals 6 we've got some issues. Coming in from the left, I'm approaching 2. From the right, I'm approaching 5. We've got that big jump in the graph there, so it's definitely discontinuous here. So it's not continuous at 6. The limit does not exist, right? We just discussed how those left and right-hand limits don't match. And then f of 6 in this case is 5, where the closed circle is. For the last one at x equals 10, you can draw your graph through x equals 10 and not pick up your pencil. And the limit and function value are both 0. So here's why we went through this example. There were 3 yeses and there were 3 nos. And I want to see if you can come up with the conditions that have to be true in order for a function to be continuous at a given value of x. There are, in fact, 3 conditions that must be true in order for you to be continuous at a given x value. So think about that for a second. We're going to fill those in just a moment. But if you think you've got them, write some of them down on the next page in that box at the top. Because we're moving today from an informal definition, which is don't pick up your pencil, So more of a formal definition of continuity. So the formal definition that I have here is, in order for a function to be continuous at x equals c, any random x value, where c is a real number, the following conditions must be met. So the first one that I wrote down that maybe wasn't as obvious based on the examples that we saw is that, well, f of c has to have a value. Okay, if you have an open circle at your x value of c, you're definitely not continuous there. What maybe was a little bit more obvious is that the limit has to exist. In cases where we got a no for continuous, some of those cases corresponded with the limit not existing. So if the limit doesn't exist at that value of x, you certainly cannot have a continuous function at that value. And then the last is kind of the most critical, is that the limit and the function value have to match. And I think the best example I can show you for that is number 2. If you take a look at number 2 from the front page, the limit as x approaches -8 existed. F of -8 also existed and has a value. So that's already met criteria 1 and 2. But since those things don't wind up matching, they're not both the same value, we say that in general, this graph is discontinuous at x equals -8. And I think that really is pretty clear looking at the graph. At x equals -8, I got to jump up here, fill that in, keep on going. So hopefully that's a good example to model that last case that has to be true in order for a function to be continuous. The limit as x approaches that value c that we want to be continuous at has to equal the function value at c. So what this is going to now lead us into is a discussion of different types of continuity. So there are 3 types of continuity, or I should actually say discontinuity. So if something is discontinuous, we want to be able to name it. So what type is it? And then once we've named it, we want to be able to justify mathematically why we're discontinuous there. So let me give you kind of a quick rundown of what we're going to see in this chart here. Okay, the first case is something called removable discontinuity. Okay, we've seen removable discontinuities before. An informal way to describe a removable discontinuity is a hole in the graph. So think about all those cases where we've found the limits by factoring and canceling. Every time you cancel those factors, top and bottom, it represents a hole in the graph. So the graph might look something like this. So we would say, yeah, the graph is discontinuous at x equals c, if we have a line with kind of just a big empty space in the middle. So what would be the reason for being discontinuous at c in this example? Well, you have to tell me which one of these 3 rules have we broken. A lot of times it will be rule 1 or 2. But in certain cases, we'll also see maybe breaking rule number 3. All right, the reason why we're discontinuous here is that f of c has no value. Okay, there's no y value that corresponds with an x value of c. So because of that, we have a discontinuity at c. If I ask you for the type, though, the type is that it's removable. Okay, so when we talk about where it's potentially discontinuous, we want to talk about type and then the reason. All right, here's our second type. Our second type of discontinuity is called infinite. An infinite discontinuity most likely is where we have an asymptote on the graph. So we've seen a bunch of scenarios where that might happen as well. So here's what we're talking about. A graph that might look something like this. The asymptote is at this x value c here. So we would say, well, yeah, this is discontinuous at x equals c because one of 2 things, actually. First of all, f of c also in this scenario does not have a value. But you could also justify in this one that the limit as x approaches c doesn't exist. As we approach c from the left and as we approach c from the right, not approaching the same value. So this one has 2 different justifications you can have for a reason. Whereas like in this one, the limit does exist. As I approach c from the left and the right, it's whatever we're getting really close to. It's getting close to the same y value. This one, not the case. And actually you can use either of these 2 reasons and be justified in your response. Finally, we have one more case to look at. The last case is called jump discontinuity. So jump discontinuity is what we typically would see, I guess, in a piecewise graph. We see jump discontinuities a lot in those scenarios. Here's a graph of what we might be referencing here. At this x value c, we have a jump discontinuity. think it's pretty clear. The name sort of implies what we have on the graph there. So what's the reason in this case? Does f of c exist? Yeah, f of c exists. Does the limit as x approaches c exist? No. So that's the reason this time. Okay, you can't use both like we did in the last case because f of c does have a value. But as I approach c from the left and as I approach c from the right, those two things don't match. So it will take a little bit of time to get used to providing some reasoning and then listing one of these three types. Okay, but we're going to try and get and do a little bit more practice with each of those cases. So let's go ahead and take a look at the examples below. It says determine the values of x for which the following are discontinuous when applicable. State the type and the reason. So type, one of these three options in the left column. Reason, a couple of these options from the right column, but the reasons are really based on one of these three cases. Which of these three rules did we break? The first example that we're going to look at is f of x equals 2x plus 3. So I want you to think about that graph. We should really know what that looks like as we finish up a course in pre-calculus, right? So is there anything that would be a removable discontinuity? Is there any asymptotes? Do we have any jumps? Is this a piecewise function? Nothing that I can think about. I mean, that's just a straight line. And a straight line is continuous everywhere. So if it's continuous, that's great. You're just going to say it's continuous over the set of real numbers, which you can write just negative infinity to infinity if you want to represent that, or fancy looking capital R, up to you. All right, so not all of these will have discontinuities. If they do, we're going to list these two things, type and reason, okay? But otherwise, we'll just say continuous over the entire domain of real numbers. What about number 2? Something with x cubed in it, x cubed plus 3x squared minus 4x plus 2. Can you imagine what that looks like? It looks maybe something like this. I don't know, any holes, asymptotes, or jumps here? I don't see any. In fact, really anything that's a polynomial function, whether it's linear, quadratic, in this case cubic, it's going to be continuous over the set of real numbers. So there's really not much to worry about in terms of the graphs of things that are polynomial functions. Okay. Well, let's get to the more exciting stuff then, or at least more exciting in the context of talking about continuity today. Let's talk about maybe something that is not always continuous over the set of real numbers. Like how about 1 over x plus 4? Okay, let me just switch this back a little bit here. Okay, 1 over x plus 4. What does that look like? Can we imagine it? Can we picture it here? Well, if you want to check it out on the calc, you can. I'm hoping that you might remember that there's kind of an issue with this one with whatever makes the bottom equal to 0. And you can set that equal to 0 and solve in this case, but this one's got a vertical asymptote at x equals -4. So if you were to sketch a graph of this, you would go to -4. It's not going to cross x equals -4. And the graph's going to wind up looking something like that, which is actually a sketch that I made for one of our types of discontinuities earlier. So now that we've had this sketch here, I want you to be able to do two things. So you're going to tell me, where is this discontinuous at? This is discontinuous at only one value of x. It's discontinuous at that x equals -4 value. But now I want you to tell me two additional pieces. Not only where is it discontinuous, but what's the type of discontinuity? And then what's the reason? Well, the types are removable, infinite, or jump. Okay, infinite is the case where we're going to list it if there's that asymptote that is what is making it discontinuous there. So the type is going to be infinite. And like I said before, whenever I talk about a reason, I'm going to talk about which of these three rules did we break. And like I showed you in this example here, we're kind of breaking two rules for this one. Okay, f of -4 doesn't have a value, and the limit as x approaches -4 does not exist. So you can actually give one or two things. You can say f of -4, okay, you want to be specific at the x value that we're saying it's discontinuous at. F of -4 equals the empty set. That's probably the easiest of the reasons. But if you wanted to get fancy, you could have also told me that the limit as x approaches -4 for my function f of x does not exist. Okay. You do not have to list both of those reasons. Either are sufficient. But in case you were thinking, hey, isn't that also a valid reason? The answer is yes. Okay, let's move on and try something like number 4. 4 and 5 are both piecewise looking defined functions here. So whenever you have piecewise, we might be thinking, potentially a jump discontinuity at some point in the process. Okay. So if we look at this example here in number 4, we've got that we're going to graph x plus 2 when x is not equal to 1. And then we're going to graph 0 when x is equal to 1. So I think that it's always a little tough to graph. I think this in general, students get confused when it's not the inequalities like we'll see in the next example. Okay, let me just focus this for a second here. Let's say we can visualize what this would look like graphically. At x equals 1, we're going to have a y value of 0. So at 1, 0, we have a point. Otherwise, everywhere else, we're going to be graphing this line x plus 2. So x plus 2 has a y-intercept at 2. If I were to plug in 1 for x here, 1 plus 2 would be a y value of 3. So on this line, you're going to have a hole here. But you're going to see that line graphed everywhere else on the grid, except at x equals 1. At x equals 1, you get that filled in closed circle at 0. So does this graph have any discontinuities? Do I have to lift up my pencil anywhere? Sure do. This is discontinuous at x equals 1. So we get this discontinuity at x equals 1. I want to list now the type and the reason that we have for this discontinuity. Okay. I kind of go back and forth with type on this one because we didn't really have enough info in advance about maybe why we had this hole here. So I'm going to define this one as a jump. I'm going to think of it as saying, hey, we have to jump down, fill in this point, and then we keep going. Although I think some teachers might also be able to justify that this is removable. We'll talk about that more in a little bit, but I'm going to say that this one's jump for now. The most important thing, though, in my opinion, is what's the reason why this one's discontinuous at x equals 1? Does f of 1 exist? We go back to some of these reasons up here. Does f of 1 have a value? Yeah, f of 1 is 0. Does the limit as x approaches 1 exist? So we said, yeah, f of 1 is good. That's 0. What about the limit as x approaches 1? Does that exist? Well, as I approach 1 from the left and as I approach 1 from the right, I'm getting closer and closer to 3. So that rule is also good. But what's the rule that's being broken? These two things don't match. In order for us to be continuous at x equals 1, those two things would have had to be the same value. So the reason is that the limit as x approaches 1 for f of x does not equal f of 1. That's the toughest reason for students to write down and remember. But when the limit and the function value don't match, that is a reason as to why we might be discontinuous. The last thing I'll say about number 5 here is number 5, you don't have to draw the graph every time. If we're thinking about where we might be discontinuous, look at the 3 functions in question. We have a quadratic, a line, and a line. Those in themselves are not discontinuous anywhere.